Welcome to this explainer. You know, if you throw a tennis ball at a solid brick wall, it just bounces right back. It doesn't have the energy to smash through, so it stops. That's just how our everyday reality works. But when we zoom down to the absolute smallest scales of the universe, those rules, well, they completely change. Down there, particles occasionally do something that seems, frankly, impossible. They pass straight through seemingly impenetrable barriers. They don't break the wall, and they don't go around it. They literally just appear on the other side. So let's dive into this and understand exactly what's going on here. To really wrap our heads around this, we have to contrast our everyday intuition with quantum reality. In classical physics, you know, the world of cars, baseballs, and us humans, a lack of energy means a hard stop. That ball bouncing off a wall is classical mechanics in action. But quantum mechanics, which is the rule book for things like electrons and atoms, plays by a totally different set of rules. In this tiny realm, a particle can approach a barrier it technically doesn't have the energy to cross, and yet it can spontaneously appear on the other side. This is what we call quantum tunneling.
To unpack all this, we'll be looking at 4 key areas today. First, the phenomenon itself. Second, why it actually happens. Third, the mechanics of how it works. And finally, its real-world impact.
All right, let's start with section 1, the quantum tunneling phenomenon, and what happens beyond the classical barrier.
We have to start by looking closely at the fundamental nature of the particles themselves. We are so deeply conditioned to think of subatomic particles, like electrons, as tiny, solid billiard balls. And if they were, tunneling truly would be impossible. But they aren't. In the quantum world, particles actually behave like waves of probability. Instead of existing at one exact pinpointed location, a particle is kind of spread out across space as a probability cloud. This cloud essentially gives us the mathematical likelihood of finding the particle in any given spot. Getting comfortable with this shift in perspective from a solid object to a probability wave, well, that's absolutely crucial to understanding everything that comes next.
Moving on to section 2, why it actually happens, and the rules of the quantum universe.
Before we get into the actual mechanics of how a particle crosses a wall, we need to establish the foundational rules at play here. The first rule is all about the wave function. In quantum mechanics, those probability clouds we just talked about are described by a wave function. Now, it's really important to keep in mind that this isn't a physical ripple, like a wave moving through a pond. It's a purely mathematical description of probability. Where the wave's amplitude is large, there's a high chance of finding the particle when we look for it. Where the amplitude is small, the chance is low. The particle's exact position simply isn't locked in until it's actually measured.
So, the second rule is the uncertainty principle. This principle reveals a fundamental trade-off in nature. Basically, the more precisely you know a particle's position, the less precisely you can know its momentum and vice versa. Because of this inescapable built-in uncertainty, particles literally cannot have perfectly sharp, rigidly defined boundaries. Their probability waves just have to spread out into the space around them, and as we'll see, it is exactly this spreading out that allows a tiny portion of a particle's wave to sort of reach beyond physical barriers.
Our third and final rule is superposition. Before we make a measurement, a quantum particle isn't forced to pick a single state. It can exist in multiple possible states all at once. So when a particle's probability wave approaches an energy barrier, it enters a superposition of outcomes. In a mathematical sense, it's being simultaneously reflected by the barrier and transmitted right through it. It's only the act of us observing or measuring it that collapses the superposition and decides which of those two realities we end up seeing.
Which brings us to section 3, how particles actually cross these barriers and the mechanism of tunneling itself.
Okay, so now that we know particles are probability waves governed by uncertainty and superposition, let's look at how they calmly navigate a physical obstacle. Picture our electron approaching a thin insulating layer. Step 1, instead of just bouncing off, its wave function extends directly into the barrier. Step 2, as it moves through the barrier, the wave rapidly shrinks in amplitude, which means the probability of finding it there is dropping fast. But step 3, if the barrier is thin enough, that wave doesn't hit absolute zero. A very small part of it emerges on the far side. Finally, step 4, when a measurement occurs and we locate the particle, there is now a real, non-zero chance that it'll be found on the other side. The particle didn't break the wall, its probability simply leaked right through it.
Now, of course, tunneling doesn't just happen randomly with everything around us. There are specific physical factors that strictly control this probability. First up is barrier thickness. Naturally, thin barriers are much easier to tunnel through because the wave function has less distance to travel before it shrinks to zero. Second is barrier height, which represents how much energy is required to cross it. Lower energy barriers increase the chance of tunneling. And third is the mass of the particle. Lighter particles, like electrons, have more spread out wave functions, so they tunnel quite readily. Protons tunnel a bit less often. And large, macroscopic objects, like baseballs or even you and me, well, our probabilities are so infinitesimally small that we will essentially never tunnel.
At this point, you might be thinking, doesn't this break the law of energy conservation? I mean, if a particle doesn't have the energy to cross a barrier, but it crosses it anyway, did it magically borrow or steal energy from nowhere?
Well, the definitive answer is no. Energy is fully conserved here. The particle has the exact same amount of energy after tunneling as it had before it even encountered the barrier. You see, quantum mechanics isn't saying the particle forcefully pushed its way through the physical material. Instead, the rules of probability just dictate that there's a chance of finding the particle on either side. So rest assured, no fundamental laws of thermodynamics are being broken today. Now for Section 4, the real-world everyday impact of all this, from the sun to your smartphone. It's honestly pretty easy to view quantum mechanics as just abstract math confined to university chalkboards. But this exact phenomenon is what builds our observable universe. Out in nature, tunneling is responsible for the sun's fusion, radioactive decay, and the creation of heavy elements. And in human engineering, we've actually harnessed this phenomenon to create flash memory for our devices, electron microscopes that can see individual atoms, and even the latest quantum computers. Let's look a bit closer at a few of these, because they're fascinating.
Perhaps the most vital example is the star at the center of our solar system. Deep inside the sun, positively charged protons naturally repel each other with immense force. Classically speaking, they just don't have enough thermal energy to get close enough to fuse. But thanks to quantum tunneling, a tiny fraction of these protons' wave functions penetrate that repulsive barrier. This allows them to get just close enough for the strong nuclear force to finally bind them together. This fusion releases the staggering amount of energy that powers the sun. So to put it simply, without tunneling, stars wouldn't shine, heavy elements wouldn't form, and well, we wouldn't be here to talk about it.
On the technological side, just think about the device you might be using to listen to this right now. Flash memory, the kind found in smartphones, USB drives, and solid-state computer drives, stores data by trapping electrons. Writing and erasing your data depends entirely on forcing those electrons to tunnel through ultra-thin insulating layers in a highly controlled manner. So literally every saved photo, every text message, and every file on your phone relies directly on this quantum effect to work. And the applications just keep going. Scanning tunneling microscopes use a sharp tip where electrons tunnel across a tiny gap, which lets scientists map the surfaces of materials atom by atom. In nature, alpha decay occurs because particles tunnel out of atomic nuclei. That's what explains radioactivity. Quantum computers use tunneling to efficiently explore complex optimization problems. But you know, it also presents a real engineering ceiling for us. As we try to make computer chip transistors smaller and smaller, the insulating barriers inside them become incredibly thin. Eventually, electrons start tunneling where they aren't supposed to, causing what we call leakage current. Right now, that's actually one of the greatest challenges in modern electronics.
And that brings us to our final takeaway. Particles doing the impossible.
Let's draw all of these ideas together. Quantum tunneling really forces us to abandon our everyday classical intuition. Our brains are built to interact with massive objects over large distances. But at the quantum scale, objects are probability waves. And because of that, the word impossible takes on a totally different meaning. In the subatomic world, impossible often just means extremely unlikely, not strictly forbidden by the laws of physics.
It's a quiet, profound truth of nature that the universe operates on probability, not just absolute solid boundaries. This seemingly impossible process isn't a glitch. It is an absolutely essential feature of our reality. So, the next time you save a photo to your phone, or simply step outside and feel the warmth of sunlight on your skin, remember exactly why it's happening. Both of those everyday experiences are only possible because, at the very foundation of reality, particles can sometimes do the impossible and pass straight through walls. Thank you so much for joining me for this explainer, and keep questioning the world around you.